Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
All right. Good morning, everybody. It's my pleasure to welcome Yiying Zhang. She's a student with the Apache Dish shows at Wisconsin, and she's interviewing for a postdoc position with the systems group. She's well decorated with several FAST papers and a Eurosys paper, and she's going to talk to us today about de-virtualization. So.
Thank you for the introduction, and thank you for coming for my talk. I'm Yiying Zhang from Wisconsin Madison. I'll be talking about de-virtualization storage systems, which is the work I did with my PhD work. So we know that virtualization is a common technique to transform physical resources into an abstract form that can be more easily accessed. And virtualization has been used in many systems. For example, physical resources, physical memory is virtualized into virtual memory to provide address spaces for different processes. And hard disks, its internal cylinders and platters are also hidden and virtualized into the logical block interface. And for the flash-based SSDs, its internal structures and operations are also virtualized and behind the same block interface. And we can see that virtualization provides simplicity, flexibility, and usually a uniform interface to different clients. And to realize virtualization, the technique of indirection is usually used by referencing an object with a different name. I think in this example, if we want to virtualize object B to A, we can add an indirection from A to B with a mapping table. And such mapping table is used widely in different systems, like page tables in virtual memory management, flash translation layers for flash-based SSDs, and also remapping tables for hard disks, and also RAID constructions. So we know that virtualization is good, but my question is, have we taken it too far? That redundant levels of virtualization is added in a single system, a problem we call excess virtualization. I think in this example, the object A could have been directly mapped to object C. Instead, two levels of virtualization are added. Such excess virtualization happens in many systems. A good example is when we run an OS on top of a hypervisor. Another example is when we run a file system on top of RAID or SSD. So each will maintain their own logical address mappings. And in all these examples, there's an information redundancy because of excess virtualization. And imagine now if we have a file system on top of virtualized, but the real problem is that there's a cost with excess virtualization. And first, we need mapping table at each virtualization layer to store the mapping tables. And these are always usually stored in main memory or the more costly device memory. And also, there's a performance cost to access and maintain the mapping tables. So we can see that excess virtualization is redundant and cost both memory and performance. And my question is there any way we can make systems work together so that we can more compactly represent the redundant information? And the technique we propose is de-virtualization, which collapses multiple levels of virtualization. I think this example, we collapse the two levels of virtualization and remove the mapping from B to C and directly map from A to C. And now imagine if we have a file system on top of a virtualized device. And first we have for a block, we first map from a file offset to logical address, use a file system data structure, and then from logical address to a physical address, use device mapping. And what we do is remove the device level mapping and directly map from file offset to physical addresses. And So with this basic idea, I first began my research with a simple hypothesis that with the write interface, we can remove the redundant virtualization. And with this hypothesis, I designed a new interface called Nameless Write. Nameless Write is like a normal write, but it only sends data and no name or logical address to a device. And then the device will allocate a physical address and returns the physical address to the file system. And then the file system will store the physical address and for future reads. And I implemented Nameless Writes with ext3 and then emulated SSD first. But then I found that Nameless Writes changed many aspects of the software, hardware, and interface. So I was curious to see if the idea still holds with the real hardware. And I built a hardware prototype on top of a testing SSD board. And then with the hardware experience, I found that there are actually many problems with the Nameless Writes interface. Basically because Nameless Writes is fundamentally difficult to integrate into the existing ATA interface. And with these ideas, I'm now building a new tool called File System De-virtualizer, which doesn't have the proper complexity of Nameless Writes and can still use the existing I/O interface. But what it does is it can dynamically change file pointers to point to physical addresses. So it will fit better for dynamically removing mapping table space. And this is an ongoing work, so I don't have satisfying results to show you. But overall, we found that de-virtualization removed device RAM space by 14 to 54%. And also, it improves random write performance by 20 times.
Percent or times?
Times, sorry. 14 to 55.
14x, can you give us a sense for the scale? Is that from 14 kilobytes to 1 kilobyte or from 14 gigabytes to 1 gigabyte?
I think it's from maybe 1 GB to, yeah, less than that. It depends on your device size, actually. So. And I also learned a set of lessons in this experience. First, with the write interface, excess virtualization can be largely removed. But adding a new interface can be hard, and also it's even more difficult with real hardwares. But with a lightweight tool, it can be done with more flexibility. So in the rest of my talk, I will first go over some background of flash-based SSDs. So the technique of de-virtualization applies to different types of storage devices, but SSD is a major use case. So I will talk more about SSDs. And then I will talk about the new interface and the software and hardware prototype of it. And then the new tool that I'm building now, and finally future work and conclusion. So I know many of you already know a lot about SSDs, and I apologize for more redundancy, but I will try to go quick. So SSD is a device that provides a block interface, and inside SSD there's a controller, an internal RAM, and a set of flash memories. And then within the flash memory, it has a set of erase blocks, and each erase block has a set of pages, and each page is associated with an out-of-band area, which stores things like valid bits. And there are three operations for flash memory: read, write, and erase. And reads and writes happen at the granularity of flash page, which is usually 2, 4, or 8 KB. And the property of flash memory is that you cannot write a flash page without erasing it. So for this example, if you want to write to the first page without erasing the first erase block, then there will be an error. And such erases happen at the granularity of erase block, which is usually 256 to 1 MB. And then with these erases, flash blocks wear out. And so with different access to different blocks, certain blocks may die sooner than the others. And to prevent certain blocks from dying too soon, the technique of wear leveling is used to make erases wear out similarly. And to virtualize SSD, flash translation layer, or FTL, is usually used to give you the block interface and to hide the internal operations. It usually uses a mapping table to map from logical address to physical address. And such mapping table is usually added at the device RAM, which is more costly in both monetary and energy. And for example, for a 1 terabyte SSD, you need 16 GB just to store the mapping table if you map at the 4 KB granularity. So instead, most modern SSDs use a hybrid mapping technique. They map a small area of page mapped area and a large area of block mapped area. And now you have 1.8 GB for a 1 terabyte disk. However, there's a performance cost because of garbage collection for the hybrid FTL. And this is the main reason for poor random write performance in SSDs. So now imagine if you have a file system on top of SSD. You first map from file offset to logical address, and then from logical address to physical address. And there's excess virtualization here. And what we do is we store physical addresses directly in file system, and then remove the mapping in the FTL. And doing so will reduce both the memory space cost and performance overhead. And also, one major thing that we want to make sure is that the device still have its critical control of this hardware, like garbage collection and wear leveling. So now I will go to the new interface, Nameless Writes work. And I'll first go through the simulation results and the major design. So this is a major architecture of Nameless Writes. So first you need to port the file system to Nameless Writes, and then have a nameless writing device. And the interface between them is a set of nameless write interfaces. So basically what it does is it returns the physical address to the file system, and then the file system stores it for future reads. So now I'll talk more details about the actual interface called Nameless Write. I'll show you with an example of how it works. So in this example, the orange block, you can think of it as a data block. And the blue block, you can think of it as an inode. So the inode points to the data block. And the file system wants to write the orange data block. So it sends only the data to the SSD and no address. And then the SSD writes it at physical address P, and then returns physical address P to the file system. The file system then stores it in its inode. And so for nameless writes, we also need a set of other interfaces to work together. For example, for reads, now we need to use the physical address P to read the data block, and we call it physical read. And also, because nameless write is an allocation process, we also need deallocation. So we use free or trim command for deallocation. So the interface that I just spoke of is quite simple and naive, but it has a set of problems with the simple interface. So first, if we use nameless writes as the only write interface, then there will be a performance cost. And also for devices like flash-based SSDs, they need to move physical blocks, and we need a way to handle it. And finally, there's a way of how we can find metadata structures efficiently. Yep.
You just said that Flash has to move the blocks. Is that, I thought that the point of this interface is to obviate that. I thought the moving was to deal with garbage collection and so on, and wear leveling, but if you're exposing allocation up a layer, why do you need to still move the blocks?
So one thing, like I said, we still want the device to control its wear leveling and garbage collection. So the device internally does garbage collection and wear leveling, but whenever it does, it changes the physical address. So it needs the file system to know. And the reason why we want the device to maintain its control is that, so one thing is that it can be dangerous if your software controls the hardware directly. And the other thing is we don't think vendors will ship things that they cannot guarantee for the wares.
Can you explain the source of the overhead you're talking about in the first bullet point? You said that if you use nameless writes for everything, then the
I will go through each of these points in turn. So to explain the first problem of the overhead of nameless writes, I will use a simple example. So imagine with a small file in the root directory, and the data block is pointed to it by its inode, which is pointed to by the root directory. And the file system wants to override orange data block. So what it does, it sends only the data to the SSD. SSD allocates physical address P0 and returns P0 to the file system. The file system then stores it in the inode. And since the inode is changed, it also needs to write to the SSD. So again, the SSD allocates P1 and returns P1 to the file system. And then the file system stores both P1 and the offset of the inode within that block P1 together to point to the inode. And since the root directory block is changed, it also needs to write it. And the SSD writes it at physical address P2. So you can see in this process, there are several problems. So the first problem is that we have an overhead of recursive updates. So originally, we only want to override the orange block. And now we have 3 writes. And also, we need to enforce the ordering in this chain of recursive updates. And imagine if we have a long directory chain. So this can go up to n writes. Another problem is that this with only nameless writes, the file system will become more complex. So originally, the inode can be pointed to by the inode number. And now we need the physical block address of the inode block and the offset of the inode within that block together to point to the inode. And also, we need a different technique to locate the root directory block. So to solve this, yeah.
Can I ask another question about this? And you push this off if I'm... But does this mean that SSD now has to maintain a free list? In other words, if you delete a file in a traditional file system, you just delete the metadata.
Right.
And then later you can rewrite the same blocks. But now it seems like the SSD would have to know which blocks can be overwritten.
Yeah, that's why we have to have that free or trim command.
Okay.
And not all file systems support that trim. So we added that trim to the file system. So to solve the first problem of recursive updates, we proposed a technique of segmented address space. So the first address space is a physical address space where we use nameless writes and physical reads. And the second address space is a virtual address space where we use traditional reads and writes. And also we need to keep an indirection table for the virtual address space. We map all the data blocks to the physical address space and all the metadata blocks to virtual address space. And notice that metadata is usually small, around 1% in the file system layout. So this mapping table for the virtual address space can also be small. And now let me explain how the segmented address space work. So we map all data blocks, which is the majority of file system, to the physical address space, and all the metadata to the virtual address space. So for the physical address space, we send only data to a device. A device allocates physical addresses for them, and then writes them to their physical locations. And after that, they return the physical addresses to the file system, and file system keeps them. And then for the virtual address space, we send both the data and their logical addresses together to the SSD. And then the SSD allocates physical address and keeps a mapping for them, and then write them to the physical locations. So now let's revisit the same problem, same example. So now we want to override the orange block, and the file system sends the data to a device. Device allocates at P0 and returns P0 to the file system. So the file system updates the inode. And now since the inode is in the virtual address space, we write both the inode block and logical block address of it, L1, together to SSD. And then SSD will allocate a physical address P1, and then it will add a mapping from L1 to P1. But now we don't need to change the root directory block because it always uses the inode number to point to the inode. So we can see that now we only have one level of update propagation. And we go from n writes to 2 writes. And with this design, it's also simpler to implement and debug. And the second, yes?
So, and I should compare that 2 writes, not to the single write of a file system talking to the device virtual interface, but to the 2 writes of the file system talking, like these 2 writes are 2 physical writes, and I should contrast them with when you had the stacked virtual address spaces, the things looked like 1 write, but the file system became more than 1 write down in the FTL. Is that why 2 writes is not bad?
So this is all writes of blocks below the file system. So what we want to do is an overwrite of the orange block. So, and the inode points to orange block. And there's a field like change times in the inode. So whenever you modify a file that inode with traditional file system, anyways it needs to write inode.
Okay, so 2 writes is already the
Yes,
RT.
right. So
the
it
inode-
goes back to 2 writes.
Won't the inode store just the block number, and if you virtualize on the block number itself, wouldn't you have had just 1 write in the previous case as well?
So the inode usually, it also has a field called change times. So you need to anyways update that file modify time.
Well, but not the
And-
indirect blocks. Usually for a large file, the inode.
Yeah, for indirect blocks, yes. So if it's not pointed directly by the inode, so if it has indirect blocks inside it, then with nameless writes, you need to update the direct up level of indirect blocks. But with traditional, you don't need to update that inode. Indirect blocks. But with ext3, we write all these metadata with a journal, so it can gather more data blocks, more metadata blocks together. But yes, there's a performance cost. So the second problem comes from the need for flash-based SSDs to migrate blocks, physical blocks, for tasks like wear leveling. And I'll show you why this can be a problem for nameless writes. So now imagine the SSD wants to do a wear leveling and moves the physical blocks from P1 to P2. After it has been moved, its old address can be erased and then can be written with new data. Yes.
You're doing this move because you want to do compaction or is
The
it
SSD needs to do wear leveling. So basically, you have different write pattern to different erase blocks, and you have different wears. And so the SSD actually
But you could do wear leveling without actually moving these blocks, right? I mean, just copy the data over, erase it.
that's what it's doing.
But don't just write it to the same one location. After erasing, when you could potentially create an erased block, write the data to the same one location, and you
But
created
then
a lot
the
of
same-
holes where other blocks can be stored.
The same location will have the same write pattern. So if that block has,
So keep the physical address of the live blocks the same, and whatever garbage blocks are there, use those holes for filling in dirty blocks.
so there are two things. One is garbage collection. The other is wear leveling. So for wear leveling, so imagine if you have a data block that has been is written very frequently. So it has hard data, and if you move it to get still it has the hard data, then it will has more and more erases.
So this,
Like P on this page.
I'm confused about this because I thought the interface of Nameless Writes is that you can't make a hot block because you can't say the file system can't say I want to write there. It says I would like to write.
Right.
And then the SSD says, well, you can write over here. So I don't understand why the SSD can't do wear leveling at the.
Because she's just reintroduced that.
Because the read has a physical address, and so you need to update the file system.
The solution to the previous problem, John, was to reintroduce a logical translation line.
I see.
For some of the blocks.
And that reintroduces heat.
Yeah.
Okay. All right.
So this is just for metadata then? This is just for the virtual, so you said you've got two partitions here, right? The physical one and the virtual one.
Right.
This is just for the virtual one, is that right?
It's whatever the device wants to do with wear leveling. So it doesn't know what is metadata and what is data. So whatever it does is whenever it sees that block is written very frequently, then it will consider it as a hot block and then swap it with some cold block. That's the basic idea. But
That goes back to John's question, which is if a hot block is in the data partition, not the metadata partition, then the solution is just to stop writing there. When another write comes down, you pick some other block to write.
Whenever a write comes down, the SSD will always pick another location. But we hope the SSD does. But internally, we don't make assumptions of whatever the SSD is doing for their wear leveling. But the main point is whenever they do, and they need to do for at least for the metadata part.
Is the idea that this is an autonomic process happening in the background? So asynchronously you have data moving around as part of the wear leveling, and that's why it has to notify asynchronously the file system, because the file system has intimate knowledge of where the data is that has to get asynchronously updated. Is that the idea?
Yeah, so basically after it moves, I will go to this now. So after it moves, your old address will be written with new data, but the file system will still think this block is at P1, so it will read P1, and then wrong data will be returned.
So can you give us an example where the device would do this? Like, so you're changing the interface to the device, but you're not changing the SSD itself.
I'm also changing the FTL, but so the FTL still needs to do wear leveling and uses, we don't change the technique of doing wear leveling from traditional SSDs. So what it does is just when it identifies a hot block, it does this wear leveling. And so that code data can be written to this block. So it needs to move data around.
It's a background maintenance process. It's happening all the time.
Yeah, it's a background.
Is it here that you're sort of inventing a new SSD that has a new interface, or that you're trying to use a new sort of file system on an existing SSD?
The interface needs to be changed, and the SSD FTL also needs to be changed. But we don't particularly change. At least we haven't changed the wear leveling algorithms. So it still use whatever. It can still use whatever it did before.
So the wear leveling is triggered from within the FTL.
Yes, yes.
And you did modify the FTL in order to modify the interface, but you did not modify that aspect of the FTL.
Right, yes.
So the suggestion that John had was something you could have done but did not do.
Right, right, yeah. Sorry, I can do this offline maybe. So whenever it does so, it needs to inform the file system of this physical address change. And the solution we propose for this is to use a new interface called migration callback. So now let's revisit the same example. The SSD moves from P1 to P2, and after it's been moved, it will add a temporary remapping entry to map from P1 to P2. And now, if the file system wants to read it, it will read P1 and it will be remapped to P2 and get the correct data. And SSD also sends this information back to the file system. And the background process in the file system will process these callback entries and then update the metadata to the new physical address. And after it's been updated, the file system will send an acknowledgement to the SSD. And then the SSD can remove the remapping table. Yes?
Does the file system have a reverse mapping of physical blocks to inodes?
No.
And how does it know where physical block 1 is?
I'll go through it. This is the third problem. So the third problem is, like you said, we need to locate the metadata that needs to be changed. And this can be needed for callbacks and recovery process. And naively, we can scan through the whole file system to find the right metadata. But of course, it's too costly. So what we use is a simple solution and what we call associated metadata. And it operates like a back pointer. So it keeps information like inode number, inode generation number, and offset. So with this information, you can find the metadata. So what it does is whenever the file system writes our data, it also sends the associated metadata to the block, to the device. And the device writes it in a adjacent location next to the data page. And this is the OOB area. And whenever it does callbacks on recovery, it uses the associated metadata to locate the right metadata block. Did that answer your question?
So for every block, you have some small amount of extra storage per block.
So the OOB area is already there. So it used to store things like valid page. It's within the flash memory. So it has a usually 128 byte area next to each 4 KB flash page.
And is this something that was previously completely private to the SSD and you've now exposed to the file system?
Yes, and I'll show you how that can be a problem. But the SSD will write the OOB, but the file system needs to assume that such OOB can be written. And also for reliability reason, actually I'll go over this now. So we make some further assumption for reliability reason. So some of you may have already noticed that there can be reliability issues within this process and the nameless write process. And what it can happen is if a crash happens during the migration callback or before the metadata block is updated, you have inconsistent metadata. And there's also other reliability issues that I will go into in details. Yes?
Sounds like you've just declared that every block that was previously 4K is now 4K plus a few bytes. You've got this little bit of extra data on the side with every block.
That's
a funny interface to have to a file system.
But that's a solution we have, and we'll see that that OOB area is already there, and it's usually 128 bytes, and I think we use around 32 bytes, something like that.
And the Flash has this data per block, and it's not already using it
Per
for
Flash
some
page.
purpose of its own.
It's using it, but we are hoping that they are not fill it. But that's a problem, and that's a big assumption that we make.
Sort of, I mean, if I'm a Flash vendor, it sounds like you've suddenly magicked up an extra few % of storage in every Flash drive that we can use for our own purposes. I'm sure if they're putting that storage there, they could be using it for something.
ECC.
Yeah.
Yeah, it's using for ECC and valid bit, but it has a larger space.
I mean, the counter argument is that if you're willing to change this interface, then maybe you're willing to change the shape of your rectangle ever so slightly, remove a couple rows and add a couple columns to give them the
Well, so here, hypothetically, couldn't the file system just, instead of using the Flash's private OOB storage, the file system could just take the device, chop off some extra space that it's not going to use to store file blocks and use that to store this kind of data?
Oh, I thought that part of the goal was to be able to do it in continuous, right?
So basically, when you read for like callbacks and other things, it can be, if you store it adjacent to the Flash page in OOB out of band area, then you can read them together, and you only pay one read. Otherwise, you need to read 2 Flash pages. But that's a big assumption that we are making here. Yes, and that's the cost your device will pay, yes.
Does that mean that the OOB currently used in service to the FTL, which then you wouldn't need, and you could repurpose for this?
It's using it, but at least as far as I know, it doesn't use the full 128 bytes.
I'm just
and
saying
FTL.
because you don't, this part of the address space, as I understand what you're saying, is not part of the is not being remapped. So maybe you could reuse the bytes that were being used for logical to physical mapping for this purpose, or is that not true?
Yes, but again, you are saying that we can store the back pointers with metadata, the virtual address space, within that space, the OOB area. Is that your suggestion?
I think I'm not being clear. I'll talk to you about it after.
Okay. So, but for these reliability issues, our basic technique is, again, to rely on the associated metadata or the back pointers. And we can use these back pointers to reconstruct metadata during a recovery. And also, a side thing is that we also keep a timestamp, which also increases the OOB requirement to find the latest version. And we have 2 requirements here. So the major requirement is that we need to atomically, first there needs to be OOB space for us to write. And then we need to atomically write OOB area and the Flash page for reliability issues. And also, this is something I won't go into detail, but if you're interested, we have a different garbage collection method, which is better for reduced migration callbacks. But we need to use NVRAM during this garbage collection cost, and I can talk more with our one-on-one. And with our reliability results show that we can recover all system crash cases. And the recovery process is 0.426 seconds for 4 GB SSD. I implemented ext3 with Nameless Writes, and we used order journal mode because it's a widely used journal mode, and also it fits Nameless Write well because it always writes metadata after data. And also we support the segmented address space, different interfaces, and migration callbacks. And the total lines of code is around 4,300. And they are existing ext3, JBD, and generic IOs. And you can see that they are more invasive than at least I originally thought.
So
Yes.
Did you have what was on the other side? Did you modify an SSD, or did you have a simulator? In other words,
I'll go into that.
Okay.
A couple of slides, I think. So to port a Nameless Write, a device to Nameless Writes, it first needs to support all the interfaces. And also, we allow the device to choose any kinds of allocation. And the specific device that I built uses log structured like allocations because it gives you more sequential like write performance. And also, it needs to maintain a small mapping table for the virtual address space and the remapping table. And also, One thing we still let the SSD control is its garbage collection and wear leveling technique, and I have some optimization for these things, and I can talk more offline. So what I built first is a pseudo block device drive in Linux to emulate the Nameless Write device, and it sits directly below the file system and talks to the file system with the Nameless Write interfaces. And it writes all the metadata and data in RAM so it can emulate the performance. And I built 3 types of FTLs. The first FTL is page level FTL. It's a log structured allocation, so it will give you ideal performance, but unrealistic in mapping table space because it maps with each 4 KB a page. And the second FTL I had is hybrid FTL, which I try to model real SSDs. And finally, I have Nameless writing SSD. So this is the mapping table space result that we have. So we used the impressions to generate typical file system images. And here I show 100 GB and 1 terabyte file system images, and the mapping table size in MB. So we can see that the page level FTL uses a lot of mapping table space. And hybrid has moderate mapping table size. And Nameless has very trivial mapping table size. And in fact, we find that Nameless Writes uses 14 to 54 times smaller mapping table than the hybrid mapping, which models the real SSDs, and 120 to 465 times smaller than page FTL, which is a performance upper bound.
So the way I should think about that savings is the terabyte of flash would have incurred the cost of buying another 2 gigs of RAM.
Right.
And this makes that almost free. So what proportion, how do those costs relate? Do we just save 10% or 5% of the cost of the device?
So the fixed cost is one thing, and the other cost is energy cost, which is more of a concern.
Do you have any idea what fraction of the energy of the device goes into the RAM?
I don't have an exact number, but I think a lot of it goes to the RAM. And it's especially true for cell phone, mobile devices. They consume more about energy, yes.
So have you looked at the model where the mapping tables are themselves pageable?
Mapping tables themselves?
Mapping tables themselves
are
pageable in the sense that
I know.
You wouldn't probably need the entire mapping table to run workload. So.
Yeah, but then we need to assume there's a small size of a working set size.
Right.
And also you still need the storage for the whole mapping table, but that's maybe a lower cost. So now I will show you the performance results, and I'll first show you the sequential and random write performance in throughput in KIOPS. And here we can see that for sequential writes, all the 3 FTLs perform similarly. And for random writes, hybrid is perform much worse than page and Nameless Writes.
Sorry, this is writing against your simulated block device in all
Yeah.
cases?
Yeah. I built all the 3 FTLs. So. And in fact,
is the simulated device slowing down RAM access to mimic?
Yeah, that's an emulate. So
just making sure that it was
right.
Sorry, I'm too slow. I have a question on the previous set of results. For the hybrid scheme, where you're splitting into the data region and the metadata region, isn't the savings dependent upon your workload?
This hybrid is not a Nameless Write hybrid.
Sorry.
Nameless Write is what I proposed.
For the Nameless Write, isn't it dependent on the workload? If I have a
Yes.
lot of files and a lot of metadata,
right.
then
That's why we use this tool called impressions. It generates typical file system images.
So, I guess what I'm wondering is if I was going to build an SSD,
Yes.
how big should I make the mapping table? Don't
You
I
can have a
to size it
fixed.
for the worst case.
You can have a fixed mapping RAM space, and then whenever it's going beyond that, it will just go to the normal flash page out to the normal flash page. But you can typically it's around 1% metadata size.
And SSDs already have that property today where they're built.
What property? Like they have a RAM, and now they have a fixed size. They can calculate for both page and hybrid. It's a fixed size mapping table space.
Yeah.
And for Nameless Write.
You've made the performance properties of the device I buy way more complicated, because today if I buy a device, it has a certain random access time and certain read performance, write performance. Mm-hmm. But in the future, if we adopt this, the performance of my device depends upon what kind of data I'm storing in it. If I'm storing lots of big files or lots and lots of little files, and I'm using the mapping table more, and now I'm paging in and out. Does that make sense?
I mean, to put a sharp point on it, we're talking about a cliff, right? When suddenly my flash device starts swapping.
My flash device starts swapping because I put too many little files and not enough big files on my file.
But maybe another way to answer it, it also hints at file system designers to have more smarter technique to reduce their metadata space.
It's not a bad thing necessarily, but it's another complexity in performance analysis.
Right. So here, overall, we found that Nameless Writes has 20 times random write throughput than hybrid FTO, and it's close to the page level FTO, which is the performance upper bound. And I also show you some macro benchmark results. This is varmail file server and web server from the FileBench suite. And here I show throughput in MB per second. And we can see that for varmail and file server, hybrid is doing much worse than the other two FTOs because varmail and file server have more random writes. And for web server, it only has less than 4% random writes, so everything performs similarly. So to summarize the Nameless Writes, at least the emulation part, we find that we use a new interface for de-virtualization, and it can reduce both mapping table space cost and performance overhead. And now I'll go to the next piece of the hardware prototype. So as a researcher, we often evaluate our ideas with emulation or simulation at a more conceptual level. And this is fine because it's a more conceptual level. And actually, this is the most common case for Flash-related research. But if you or someone wants to actually build a thing, it can be more complicated. So to transform ideas to reality, we can see there are many differences. So first, real hardware is more complex. And then the real interface can be different. And even the software stack to the hardware can be different. And actually, Nameless Writes change all these three parts. So it would be good to see if the ideas still hold with real hardware. And as a person myself, I was also curious and excited to build a real hardware prototype because I haven't done this before. So I had this testing board, SSD testing board. What it has a Intelix barefoot ARM SSD controller and the internal 64 MB DRAM and a set of flash chips. And the interface to host is SATA 2.0 interface. And it also has a couple of serial ports for debugging. So now what we need to do is to transform emulation to reality. And so we can see that reality is more complex than emulation. So below the file system, there's block layer, SCSI layer, ATA layer, and HCI driver. And then finally, there's a SATA interface to the SATA SSD device. And also in different layers, there can be command queues and I/O schedulers. So now what we need to do is to map the Nameless Write interface to the whole OS stack. And also we need to build the SSD emulator to a real device. So my first design is to build a Nameless Write FTO at the hardware device and work everything else towards it. And then I found a set of problems with this design and moved to the second design, which placed most of the Nameless Write functionality in OS and then have a raw firmware with the device. So I'll go through the problems that I had with the first design and then come back to the second design to show you why it works well. But before going further, I'm sorry that again giving you some background on SATA. So basically what SATA has, it has a stack of layers, and the top layer is a software layer which can be controlled by host and device. And lower layers are more related to hardware and does the actual physical communication. But all we need to know is that the lower layers are in host and device ports and cannot be changed. And the top layer talks with the ATA's command standards and can be changed. This standard cannot be changed, but the top layer can be changed. So I'll talk more about the ATA command standard. So for ATA command, there's a first set of non-data commands. So it sends from host to device the command, and then optionally LBA size and features. And then from device to host, the status, and then optionally LBA size, and if there's an error, the error bit. And for the actual I/O, it supports PIO and DMA. And from host to device, it sends command LBA size and the data to be written. And from device to host, it has status, data to be read, and if there's an error, the error bit, and the first logical block address that has an error. So now I'll go to the problems that we need to solve to build a nameless write FTO with the hardware. So the first problem we have is we need to add new command types. And then another problem is that we need to return physical addresses back to the file system. And also we need to integrate the migration callbacks into the interface. And finally, there are some consistency problems. So I'll go over each of these in turn, but maybe quickly for the easier one. So this one is much easier. So what we need to do with a new hardware interface is we just add a flag in the OS. And for device, we use the highest 2 bits in the size field to represent a new command type. And the second problem is that for nameless writes, we need to return physical addresses. And this is a more severe problem because there's no ATA. Yes?
So, just clarifying question, nameless writes is not something that has been specified or standardized out to hardware level before.
Okay. No. So basically, the ATA command standard, it doesn't support any address return back in the return path. And our first attempt is to repurpose the error return. So if you remember the error, it will send the first logical block address that has an error. So instead, we can just send a physical address. So this seems viable, but whenever the device sets an error bit, the device will freeze. And our second attempt is to repurpose a special non-data ATA command. And this is called the read native max address, which is only a command that's expecting the address. So it's expecting the maximum address of a device. But instead, we can just send a physical address back. And then with this physical address, send a nameless write. But there's also a problem with the second attempt. So first is we now use 2 commands for each nameless write command, nameless write function. And also, there's a danger of silent data corruption. Yes?
Why does the device freeze just because it returns an error?
I'm not sure, but every time whenever it sets a error interrupt, the device just freezes. At least with that board. Maybe it's not true for all the board.
So basically, the first one, read native max address, is effectively like allocating the region and the physical address, and the next one sends the write down.
Right.
So if I have lots of these happening at the same time, how do I associate?
That's why there's a.
You'll get to that. Okay.
That's why there's a silent data corruption
okay.
problem.
So it's only one write at a time.
So imagine if you have you allocate 2 sectors in the same flash page, but then you have different processes and you have different scheduler at different places. So finally, when the nameless write happens, you can write the same page twice, and again, that's why you can have silent data corruption. And the next problem is even more difficult, that we need to send the address back from the device to the host with migration callback. And one possible solution is to piggyback with other return, but then again, it has the same problem as the last problem. And another option is the OS can poll for this migration callbacks, but it's more costly in performance. And finally, there are some device-related assumptions that didn't hold for, like the OOB area that we required. The actual hardware, actually, the FTO doesn't have the access to the OOB area, at least for that board. So it has an OOB area, but it's automatically, with the hardware, doing the EEC and other things. So we don't have access to that, and there's no automatic writes, yes.
Did you consider changing the firmware to add custom IO tables?
So this is the firmware that we are changing. But there's also like a more.
My question is, why did you stick to this, like the standard SATA interface? Why did you?
Yeah, that's my next design.
Why not? Yeah. USB or something might cause you less headache.
Yeah, PCI.
Just
Yeah.
encapsulate your own protocol.
Yeah.
Yeah.
RS-232, if we're going to do it all.
So one thing that I won't cover in the slides is that you can probably use PCIe and more RPC-like cores. But I have another design with stuck with the ATA interface. But this is more, we suspect that these are more specific to the, this hardware board and may not be held with real hardware. So we can see that the first design doesn't work. And that's why I moved to the second design. And the second design places most of the, I'll talk about this design. So it places most of the nameless write functionality in the OS. And then all the interface between the file system and this block layer nameless write FTL. So everything can be done in software. And it sends only raw commands to the device. Raw commands include flash page reads and writes and flash block erases. And these raw commands can be easily built with ATA, and it's also easier to implement and debug. But there can also be danger in this design if we are not careful. So at first, what I did is I placed the nameless write FTO on top of the I/O scheduler. So what it can happen is that it can again write the same page twice without erasing it, because the I/O scheduler is below the FTL. And then there will be a silent data corruption. So, and next what I did is to move the I/O scheduler above the FTL. And then I also make sure that there's only, because FTO does allocation after the I/O scheduler, so I can make sure that there's at most one write per page. And also I have a special I/O scheduler that's designed for nameless write. Basically it can merge any kinds of writes, because the nameless write FTO will anyway allocate the physical addresses. And this is a performance result. We show sequential random write and sequential and random reads. And this is throughput per KIOPS. You can see that in some cases, nameless write is outperforming the page level FTL. This is because the special I/O scheduler that I had. But overall, we found that nameless write performs similarly as the page level FTL. And for the mapping table size, we have the similar conclusion, that it's much smaller than page table size, page FTL. So with this hardware design, I learned several lessons. So first, adding a new command is quite easy, but adding information in device return path and adding any information initiated from device is much difficult. And also, there are certain assumptions that may not hold with hardware. But most of these are because fitting nameless write interfaces into ATA protocol is fundamentally hard. And that's why I moved to the second design of the split FTL. And this way, with moving the FTL functionality mostly to low stack, we can make things much easier. But there's a dangerous that the device loses its control and let the software control its internal hardware, like the I/O scheduler example. And also, because we are placing the FTL in OS, it will consume more host CPU. So to conclude nameless write, with nameless write, we can see that a large part of the excess virtualization can be removed. And it improves both mapping table space, energy cost, and performance overhead. But it's hard to integrate nameless write into the ATA interfaces. And it also requires fundamental changes to the firmware and file system and the OS stack. So now I'll talk about the last piece that I'm working on now. So the first motivation why we need yet a different technique to perform de-virtualization is to reduce complexity as what the nameless write has. So ideally, we want to have no file system changes, no device changes, and it can still work with the current I/O interface. And the second motivation is slightly different use case. So originally, when we designed nameless write in mind, we had this hardware in mind that the hardware maintains the mapping table indirection layer. But now what many systems have is it has a software layer to maintain the indirection tables. And whenever the storage device needs more mapping table space, it will contact the OS or the hypervisor to allocate more memory for it. So in this situation, we want to have a more dynamic way to reduce the de-virtualization and the mapping table size. And also, we want to do it whenever needed without the complexity of nameless writes. So that's why I built this tool called File System De-virtualizer, or FSDV. So what it does is, normally, everything works as traditionally. So there's a device virtualization layer. It can be in software or it can be in the storage device. And then the file system talks with it with normal block interface. And also it keeps a mapping table around. And periodically, or whenever needed, FSDV is invoked. And it talks with a storage device with normal I/O and simple command to the virtualization layer. And after FSDV is invoked, the mapping table can be removed. So what FSDV does is that it changes file system pointers from logical pointers to point to physical addresses. And doing so will require small file system changes, small device changes. And it can still use normal I/O interface. So I'll show you how it works with this example. So first imagine the offline process that the FSDV first unmount the file system and then process individual files and then finally mount the file system. So in this example, there's an inode and then some indirect blocks and then finally data blocks. And what it does is it looks at the pointers and changes them from logical to physical from bottom up. So it will first look at the bottom layer. And then it will ask the virtualizer layer what's the physical address for L1. So the virtualization layer returns P1 to the file system, and then file system to FSDV. And then FSDV changes pointer to P1. And similarly from L2 to P2. And then the indirect block is changed to point to P1 and P2. And after it's been changed, the FSDV will write this block to the device. And then the virtualization layer can remove the mappings. And similarly for P3, and also for the other trees, the part of the trees. And finally, the top level inode, and then it can remove the final mapping. And we also keep a log for consistency. And this process, yes?
So would the savings depend on the kind of data structure you use for LBA to PBA mapping? For example, if you use something like a page table, then, I mean, removing only a few of those won't actually lead to a lot of savings because you still need to store the entire page containing the mapping. So what is the kind of data structure that you're using for LBA to PBA mappings that you know?
This mapping table size? It's just a mapping table for the device virtualization. It's a virtualized device, so it will keep its internal, either the device or some virtualization layer for the device. We keep a mapping from logical address to physical address.
Let's take this.
So the process I just outlined is an offline process, but it has more performance overhead. So what I did is to make it perform online, and that's the part that I'm working on now. So basically, the first optimization that I had is it will only process the changed files from the last run. So from the last run of FSDV, it will keep a record of what files have been changed and only process those files in the next run. And another online process that we have is to allow foreground IOs perform while FSDV is running. So what FSDV does is it only processes files that are closed and not in page cache. And also whenever it's processing a file, it will block all the IOs to that file. So to summarize the FSDV work, we propose a simple tool for de-virtualization by changing file system pointers to point to physical addresses. It requires small changes to file systems, small changes to device, and it can still use normal I/O interfaces. And now I'll present some of my other work and future work and finally conclude. So the part that I talked about just now is about de-virtualization of single flash-based SSDs. So what can happen is that we can have flash-based arrays. And one problem that I looked at is correlated failure. So imagine if we have mirrored SSDs, and the mirroring pair will receive the same write patterns. So they will die at the same time. So what I did here is just to add some dummy writes, what we call dummy writes, so that one device can fail sooner than the other one. And another work that I did when I was interning with Microsoft Research is duplicate aware arrays, which uses inherent duplications for availability and reliability issues. And also, Flash can be used as a cache. So I helped with the project of solid-state cache. And also, there's a problem of storage-level cache warm-up. So basically, when you have a large SSD cache, which can be hundreds of GBs, and you need to warm that up. So on-demand warm-up doesn't work anymore. So I had some analysis of data and some tools to make cache warm-up much faster. And for future work, I've been thinking about mainly two directions. So the first is the continuing of this identification and removal of excess redundancy. So what Nameless Writes and FSDV does is to remove the redundancy in pointers or mappings. And there can be also other kinds of pointers, like in deduplication, or other kinds of devices that has a virtualized indirection layer, like shingle disk. I don't know if you are familiar with that. And also, there's a content redundancy, which has been looked a lot before. But one new thing, I think it's kind of interesting, is algorithmic redundancy. So think if you have a lot of layers, and if you have, say, I/O schedulers at different layers, they can be redundant, or even worse, contradictory. So all these are because we have more and more complex software stack and hardware. So there will always be some redundancy there. And another direction that I've been thinking about is new abstraction and interface. And for things like storage class memory, software-defined storage. And what I think is the interface should be more customizable. And also, by exposing the right amount of information from the lower layer can be beneficial. I can talk more about these things offline. And finally, to conclude, let me use a famous quote that all problems in computer science can be solved by adding another level of indirection, which is usually attributed to Butler Lamson, who actually attributes it to David Wheeler. And David Wheeler usually adds, but that usually will create another problem. And that problem is excess virtualization or indirection. So to solve this problem, I first proposed an interface called Nameless Writes and built an emulation and the hardware prototype for Nameless Writes. And now I'm working on this file system de-virtualization tool, which is a lightweight tool which doesn't have the complexity and fix more dynamic situations. And it improves both space and performance. And to finally conclude, the first thing I want to say is, in my PhD experience, I find that reality is important. So it can be, it looks like everybody knows. But it can be more different from your research. And even if you don't want to actually build the real thing, it's always good to know the reality so that you can maybe say to others how you may want to build this. And another aspect is theory, which is more recently what I've been thinking. Is there any information theory behind this redundancy of X? X can be anything. And I'm welcome to more discussion along this line. Thank you. Questions?
I had a question about the online FSDVs. You can go back to that slide, the one after the offline one, the one where it actually is in a running system where files are changing. And while you're getting there, so is there a, while it's running, the file system has an idea of where some files are, where other files are, and there's a process where some files, its mapping pointers are pointing to the physical addresses, and other ones are still logical, the ones that are actively. And how can you do this without changing the file system?
So there's only one small change that we need. So you point out that a block address can both be logical and physical if you're not careful. So basically, we offset the whole physical address to the next offset. So basically, if you have a 100 GB device, so 0 to 100 GB is logical, represents logical address space, and 100 to 200 GB is for physical address space.
Okay, so they both map to the same actual cell on the
Yes, yes. But device, whenever it sees it's beyond 100, it knows that it's a physical address.
But you've got to go in and fiddle with the memory, the mapping information of the file system while it's mounted.
Yes.
Yeah. file systems don't tend to take kindly to that. But it's still really fascinating.
And you assume that you see in the page cache all instances of blocks that might be cached in any way by the file system. So if the file system implemented its own cache, or the file system kept it pointed to a logical block hanging around somewhere in a variable that wasn't in the page cache, then all bets are off.
Yeah, first, this part is I'm still working on, but at least now I'm only looking at page cache and also files that are closed. At least the function path that I've seen, they all put it in page cache.
So I just wanted to go back to deleting files briefly. It still seems like if you delete a file, the file system would have to go back and manually or explicitly mark every block that you see in the file as free.
So you're talking about the bitmap.
About?
Is it the bitmap that file system is using?
Well, in a current file system, if you have a big file and you delete it,
right,
then the file system just does some metadata updates, maybe just writes a new inode.
That's a bitmap.
But then when you try to write a new file on top of the old space, you can just issue writes to those old blocks. The old blocks get overwritten.
Right.
It's fine because that file's been deleted.
Right.
But with the nameless writes, where the SSD is picking where to write, it has to know that the block is allowed to be overwritten. So it seems like when you delete a file, you have to go through and the interface would have to change so that when a big file is deleted, millions of block deletion requests go down to the SSD to mark all those blocks as free.
So at least the way I implemented this, it collects a set of blocks that has been deleted and then sends it to the device. So the device will only invalidate when the actual physical address, whenever it receives this what we call trim or free command.
Look, a trim it's not like a truncate. What's the difference between trim and delete?
The file system, NTFS sends trim commands down when it goes and during a checkpoint goes and marks the bits out of the bitmap. It was done for SSD performance.
Trim is just a silly name.
Yeah.
Okay.
It's literally device data attribute set.
Okay.
It's a block level.
Yeah. It's a block.
Okay.
But for the bitmaps, it doesn't need to change. Actually, we don't actually use bitmaps anymore, other than for the virtual address space. So it only needs to know how many blocks it has been allocated, so that it doesn't exceed the total amount. So there's only this trim command that doesn't send the actual data. It's only telling the device which blocks you can free.
Okay. I had another quick question about so it seems like you're saying the major benefit was that we're using less RAM. And you showed some RAM comparison numbers. There were a couple things that I wasn't sure if you were accounting for. One is you're taking away some data structures, but you're adding some new ones. So did that comparison account for the fact that there was extra metadata being kept around in your scheme that the original scheme didn't need?
So there are two places you keep. So one is the internal DRAM, which the mapping table has to be sit there all the time, at least for the hot working set. And the other thing is the OOB area, which we use for storing associated metadata. It doesn't need to be accessed all the time. It only needs to be accessed whenever there's a callback or whenever there's a recovery. So it doesn't need to be loaded into the RAM. And it's cheaper with flash than with the internal DRAM.
Also, the SSD would need, you can't get rid of the entire mapping table because you still need the mapping table for the portion that's used for the inodes and things. So
right.
Did what ratio of data to metadata was that comparison assuming?
The results I used is these true impressions. So it has different types of file system layout, but usually it's less than 10%, so 1 to 10%. And that depends, so that will decide how much space you need for nameless write for the mapping table size.
Have you heard about this new type of hard drive, which is combination of SSD and low HDD, and their associated hint command with that hard drive? And have you heard about hint command?
Hint?
Hint is a new command set.
I haven't.
So
I have heard of the hybrid, but I haven't heard the hint command.
Hint is basically, like trim. It's another hint from the OS to the hard drive, saying certain area is hot than others. So for example, trim is basically says, I'm not going to use this area anymore.
Yeah.
Hint is basically says, this area is going to be used more often.
Okay.
For those, basically, that kind of hybrid hard drive, what do you think file system basically may adapt to to use them more efficiently.
What do you mean? You are saying file system may adopt to?
What I'm basically meaning is there anything else file system should do to use those hybrid drives more efficiently?
So one thing, first the hybrid drive, it can probably detect the temperature of the data themselves, but if you have more file system support. And one thing I think can maybe improve the performance is that for the SSD part, it has some internal operations like while leveling up to collection. It can tell the file system whenever it's doing so. So the file system can schedule things differently. Did that answer? Okay.
Right. Well, thanks, Ying.
Thank you.